Hello, in this session we will discuss about consecutive reaction. We will consider a general consecutive reaction where reactant A is forming intermediate I, further the intermediate I is forming product P. The rate constant for formation of intermediate I is Ka and rate constant for formation of product P from intermediate I is Kb. We will further assume that at the zero time or at the initial state of reaction there is no I or the intermediate and there is no P or the product, means the concentration of intermediate I and concentration of product P at zero time is 0 and only the reactant A exists at the zero time of the reaction. With these conditions, if we will apply the rate law expression for A, I can write dA over dt is equal to minus Ka A, because A is decreasing with respect to time, that's why it is a negative quantity. Similarly, if I write the rate law expression for intermediate I is forming with respect to Ka and it is deteriorating with respect to Kb. So it will be a positive quantity when it is associated with Ka and negative quantity when it is associated with Kb. So Ka minus Kb I. So this is the rate law expression for intermediate I. Similarly, the rate law expression for product P will be Kbi. Product P is only forming with respect to Kb and the concentration from which it is forming is intermediate I. That's why the rate law expression for product P is Kbi. So for this general consecutive reaction, we'll estimate the concentration of A, the concentration of I and the concentration of product P at different stages of reaction. Means what will be the concentration of reactant, intermediate and product at any time of the reaction. We'll evaluate that. We'll first start with the reactant A, then we'll evaluate for intermediate I, then we'll evaluate for product P. So to start with the reactant A, to know what is the reactant concentration at any time t, we have to integrate the rate law expression for the reactant A. So if we do the integration for rate law expression for reactant A, we can get an expression like equation 9. This is the same as first order rate expression we have already done, and the expression, if we integrate the rate law expression for reactant A, we'll get A is equal to A0, that is the initial concentration of A, e to the power minus K1 Ka. Ka is the rate constant for decay of A. So this integration we already know from our first order reaction kinetics. So we have obtained an expression for reactant A at any time t. Now we will obtain an expression for intermediate I at any time t. So for that we have to use the rate law expression for intermediate I and we have to integrate that. So the rate law expression for intermediate I is Ka minus Kbi. Instead of A, I will substitute my equation 9, that is A0 e to the power minus Kat. So by doing this substitution, I am getting rid of a variable. So I am getting rid of the variable A and I am substituting that with respect to A0 e to the power minus Kat. A0 is a constant quantity. So if I rearrange, I will get dI over dt plus Kbi is equal to Ka A0 e to the power minus Kat. So this is a differential equation. We have to integrate it to obtain a value for intermediate I so that we can find out the concentration of intermediate I at any time t. So the solution of this first order differential equation is of the form dy over dx plus y fx is equal to gx. So this differential expression for I is of the form dy over dx plus y fx is equal to gx. If this is the form, then the solution of this differential equation is e to the power integration fx y is equal to e to the power integration of fx dx gx dx plus constant. So there are many parameters here. To simplify, I can say for our case, this is a standard integral, standard differential expression and the corresponding solution. For our differential expression, the corresponding notions are y is equal to I, fx will be kb, that is a constant, fx is not a variable for our case, and dx will be dt, gx will be Ka a0 e to the power minus Kat. If we substitute these parameters in this integration in the standard integral form, we'll get an expression for I. Further, we have to substitute the condition that the initial concentration of I is 0. So we'll get an expression for I, and that is Ka over Kb minus Ka e to the power minus Kat minus e to the power minus kbt a0. That is the equation 10. So we are getting an expression for intermediate concentration at any time t. So we have obtained an expression for reactant concentration and intermediate concentration. Now we will obtain an expression for product concentration. I can say that the initial concentration of reactant, that is A0, is equal to reactant concentration after time t plus intermediate concentration after time t plus product concentration after time t. So if I rearrange in form of product concentration, I will get A0 minus A minus I. So if I substitute, this is product concentration is equal to reactant concentration at 0 time minus reactant concentration minus intermediate concentration. A0 is a constant term. I have obtained an expression for A, that is equation 9. In equation 9 we have obtained an expression for reactant concentration, and in equation 10 we have obtained an expression for intermediate concentration. If I substitute all those expressions, I will get my expression for P, that is product concentration at any time t. So we have obtained all the three expressions for all the three quantities, that is the reactant, intermediate and product after certain time t. So we will understand this phenomena in a graphical manner. A is forming I and further I is forming P. This is a general expression. The rate constants are Ka and Ki. Ka is the rate constant for formation of I, intermediate, and Ki is the rate constant for formation of P. We will consider three different conditions. Suppose in first case, Ka is equal to 2 Ki, means the formation of intermediate is faster than the decomposition of intermediate. In such a case, the intermediate concentration will be first A will be decreasing exponentially. A will decrease exponentially. Then intermediate will form. As long as A decreases, intermediate will form. Further, intermediate will also form product P. So after certain time t, the product concentration will start forming. Now the condition is Ka is equal to 2 Ki. We'll compare this condition with another condition, that is in a case where Ka is equal to 8 Ki, means Ki is small in this case, means the rate of formation of product is slow in the second graph compared to the first graph. What does that mean? That means intermediate, the decay of intermediate is slow in the second case, means intermediate decay to the product is slow. That's why we get a larger amount of intermediate in the second case compared to the first case. In first case, intermediate is decaying at a faster rate compared to the second case. Similarly, we will consider another case where Ka is equal to 0.25 Ki, means the rate constant for formation of intermediate, is small, but the rate constant for formation of product is large. In this third case, intermediate concentration will be very low. As long as intermediate forms, it immediately decays to give the product P. So the intermediate concentration will rise for some time, then it will decrease, keep on decreasing, because the decay of intermediate is faster compared to its formation. So there can be various conditions possible. We'll discuss two special conditions pertaining to this consecutive reaction, and those conditions are called steady state approximation and pre-equilibrium approximation. We'll discuss them shortly, and those conditions are applicable to these two quantities only, how the intermediate is decaying and how the intermediate is forming. On the basis of these two conditions, we can have two approximations. We'll discuss that shortly. From the above figure, it can be concluded that if the intermediate undergoes decays at a faster rate than the rate at which it is being formed, then the intermediate concentration will be small. This is the third case. If the intermediate decays at a faster rate compared to its formation, then the intermediate concentration will be small. Here the intermediate concentration is small compared to the reactant and product concentration. And when this is the intermediate concentration is small, when intermediate decays at a faster rate compared to its rate of formation. Then what is the maximum intermediate concentration? To know the maximum intermediate concentration, what happens with the intermediate first forms for a certain time, then after that time it decreases to form product P. In all the three graphs we have seen, intermediate forms, then it falls back, intermediate forms and it decays, falls and decays. So what is the maximum intermediate concentration? Means maximum amount of intermediate that can be formed. To know that, we have to do a differentiation. We have to know the maximum intermediate concentration, we can take differentiation of I, that is the intermediate concentration. We have obtained an expression for intermediate concentration. So we have to differentiate that expression for intermediate concentration with respect to time, and we have to set that time is T max, and the total value we have to set equal to 0. So if we do that, d over dt, and intermediate concentration we have already obtained in equation 10. So equation 10 I have substituted here. Time is replaced as T max and the expression is set equal to 0. So Ka over Kb minus K is constant. Differentiation of a constant is a 0. So this can be ignored. So the remaining term is d over dt is equal to e to the power minus Kat minus e to the power minus Kbt. Again a0 is a constant, so it will vanish. So differentiation of this exponential term at T max, that is time at which intermediate concentration is maximum, is equal to 0. So after taking then I'll set my T as T max, then I'll take the differentiation. This is simple differentiation. Then some rearrangements I have done and natural logarithm I have taken. So if we, and all are set equal to 0, if we rearrange, we can find out the expression for T max, that is the time at which intermediate concentration is maximum, and that expression comes out to be 1 over Ka minus Kb ln Ka over Kb. So this equation 11 is an expression, it shows the time at which the intermediate concentration will be maximum, and this expression depends upon two factors, that is the rate constant at which the intermediate is forming and the rate constant at which the intermediate is decaying. And obviously that is the obvious thing, intermediate depends upon two factors, the rate constant of its formation and the rate constant of its deterioration. Then the rate determining step, there are two steps are involving in our general expression. We have seen intermediate is forming and intermediate is again deteriorating or decaying. So what is the rate determining step? The rate determining step is the slow step of the reaction. The rate of product formation in a sequential reaction depends upon time scale of production and decay of a intermediate species. Means the rate depends upon how the intermediate is forming and how the intermediate is decaying, and the slow step will inform about the rate determining step. We will consider the two cases. We will consider two cases where in the first case we will consider that Kb is greater than Ka, means the rate constant at which intermediate is decaying is faster compared to the rate constant at which it is forming. So under this limit, any intermediate, this limit says what? The intermediate will immediately decay to the product. So any intermediate form will rapidly go towards product formation, and rate of product formation depends upon rate of reactant decay. Because Kb is much larger, so intermediate will immediately form product, and the rate of product formation will depend upon Ka. How rate of product formation depends upon Ka? For this case 1, we will see that mathematically. For our first case, Kb is greater than Ka. So under such condition, e to the power minus Kbt will be very less than e to the power minus Kat. These exponential terms are appearing in the intermediate expression or product expression. We have already obtained a product expression. In our just now we have already obtained an expression for product concentration. This is the expression for product concentration. So we'll use this expression there. So, and the limiting condition is Kb is greater than Ka. So under this limiting condition, e to the power minus Kat is larger and e to the power minus Kbt is much smaller. So this the first quantity of the numerator will vanish, and the whole expression will be simplified to 1 minus e to the power minus kat. Kat will be surviving because this is the larger quantity that will be surviving. And what happens, the product concentration follows a first order kind of decay expression, is identical to that predicted for first order decay of reactant A. That is the product formation. As I said, when Kb is much larger, intermediate will immediately form product P. So the formation of product P will only depend upon Ka and only will behave as a first order decay kinetics, will follow the first order decay kinetics and depend upon Ka. So here also the product is the concentration of product concentration depends upon only Ka when Kb is much larger than Ka. The opposite case will say that Ka is greater than Kb. Ka is much greater than Kb. What does this limit means? What does this condition means? This condition means intermediate is forming at a faster rate, but it is deteriorating at a slower rate. Means the intermediate to product formation step is the slow step of the reaction. Under such condition, the rate of product formation will depend upon Kb only. It will not depend upon Ka. So again, the product formation, product concentration expression will substitute this condition. When Ka is much greater than Kb, we can say that e to the power minus Kt is smaller than e to the power minus Kbt. So we can ignore e to the power minus Kt, that is the second expression of the numerator. So the complicated looking expression can be simplified as e to the power minus Kbt A0. That is, the product concentration depends upon only Kbt. That is the slow step of the reaction. So then we'll discuss a special condition called steady state approximation. What is steady state approximation? We'll see. We'll again consider the same general expression, A forming intermediate I and intermediate I is again forming product P. These are the Ratelaw expressions for reactant A, intermediate I and product P. I have already explained the Ratelaw expression, so I will not explain. Now when the steady state approximation is applicable, when Kb is much greater than Ka. Again I am saying, when Kb is much greater than Ka, that is the rate, the decay of intermediate is larger than the formation of intermediate. Under such condition, steady state approximation is valid. So we will see some important points of steady state approximation. After an initial time period, what happens to the intermediate concentration? Intermediate concentration first rises, then falls. So after an initial induction period, time during which the intermediate concentration rises from 0, and during the major part of the reaction, the rate of change of intermediate concentration of all the reaction intermediate is negligibly small. Means intermediate rises to a certain extent, to a maximum value, then it falls and it remains almost constant for a whole of the reaction. So under such condition, we can approximate the steady state approximation condition. We can use the steady state approximation condition. Again, I am repeating the condition where intermediate rises to a certain maximum value, then it decreases, and after some time the intermediate is not at all changing. The concentration of intermediate is not at all changing with respect to time. Under such condition, we can say that steady state approximation is valid. Therefore, the time that change is after certain time t, the intermediate is not changing with respect to time, or the change in intermediate concentration with respect to time is 0. So I can say the time derivative of intermediate concentration is almost 0. So this is again steady state approximation. Now to explain in terms of the rate constants, I can say that Kb is much greater than Ka. What does this mean? This means the decay rate of intermediate is greater than rate of its production. Means the rate at which intermediate decays to product is much higher than the rate at which the intermediate is forming. Under such condition only, we can say that the steady state approximation condition applies. So two things of importance to note in under steady state approximation condition: Kb is greater than Ka, that is the decay of intermediate is much higher than its formation. Further, after certain time t, we can say that the rate of change of intermediate concentration with respect to time is almost 0. So I can substitute di over dt is equal to 0. Di over dt is the rate law expression. So instead of di over dt, I can also write ka a minus kbi. We have already explained the rate law expression for intermediate. So ka a minus kbi. So instead of di over dt, I can write ka a minus kbi is equal to 0. So if I rearrange, I will get an expression for intermediate. So intermediate is ka over kb into a. Now a expression can be replaced as a0 e to the power minus kat. You have already obtained this expression, a is equal to a0 e to the power minus kat. So this is the expression for intermediate. Now what is the expression for formation of product? Dp over dt is equal to kbi, means product formation, rate law for product formation. So instead of I'll substitute the intermediate expression. I'll get this kb and kb term will cancelled out. I'll get ka a0 e to the power minus kat. So to know the product concentration at any time t, I have to integrate this differential expression. So if I integrate, and what will be the integration limit? I am considering product for so at 0 time the product concentration is 0. After certain time t, the product concentration is p. So my integration limits for product is 0 to p, because at 0 time there was no product, and for time it is 0 to time t. If I do the integration, I'll get an expression for product p. Again, this product p is also a fast order, follows a fast order decay kinetics, and the kinetics depends upon only Ka, that is the rate constant for formation of the intermediate. It is independent of the rate constant for formation of rate constant for decay of intermediate, that is Kb. So this is the expression for product P. This is the expression for product P. The last expression is the expression for product P under steady state approximation. Again, what is steady state approximation? Two conditions to remember. That is, the first condition is the decay of intermediate is much faster than its formation, that is Kb is much greater than Ka. And the second condition is after certain time t, the rate at which the intermediate concentration changes with respect to time is 0, means intermediate is not at all changing with respect to time. So we will further understand this steady state approximation with respect to a graph. So reactant is decreasing, intermediate is forming with respect to time, it rises to a certain level, then after certain time intermediate is not at all changing, it is almost parallel to the y-axis as time progresses. So under this kind of condition, and product is forming with respect to time. First reactant forms intermediate, intermediate forms product. Intermediate, the rate at which intermediate forms is small, and the rate at which intermediate forms product is much larger. So intermediate, so we are not at all seeing a variation in intermediate, because as soon as intermediate forms, it forms the product. So that's why intermediate almost remains constant, and the intermediate concentration is not at all changing with respect to time. So this graph is a perfect depiction of steady state approximation. Then we will discuss another approximation called pre-equilibrium approximation. Suppose we'll consider a general reaction where A forms intermediate I, and further the intermediate I forms product P. But let's consider a more complex reaction where the reactant A and intermediate I are also in equilibrium. In the previous case, there were no equilibrium between the reactant and intermediate, but suppose there is a reaction where the reactant and intermediate I exist in equilibrium with each other, in dynamic equilibrium with each other. Then under such condition, we can say that pre-equilibrium approximation condition can be applied, but pre-equilibrium approximation condition applies only when Ka, that is the rate constant for formation of intermediate, again I am repeating, Ka, that is the rate constant for formation of intermediate, is higher compared to Kb. Otherwise, I can also write the reverse rate means the rate at which intermediate forms reactant A. the reverse rate, that is the rate constant at which intermediate I forms reactant A is higher compared to the rate constant at which intermediate forms product P. Again I am repeating, pre-equilibrium condition is applicable when when the intermediate prefers to form the reactant compared to the formation of product product P. Intermediate has two options, either it can form A or it can form product P. So when the intermediate prefers to form A, when the intermediate prefers to form reactant A compared to product P, under such condition pre-equilibrium approximation is applicable. When was steady state approximation was applicable? When intermediate prefers to form product P. When Kb was much larger than Ka, at that condition steady state approximation was valid. But when K minus A, that is the reverse rate of formation of reactant A from intermediate I, is much larger than Kb, under such condition I can say that pre-equilibrium condition is, or pre-equilibrium approximation is applicable. What is pre-equilibrium approximation? As the name suggests, means the reaction is not at all going towards product side, rather A and I are enjoying an equilibrium state, means they are experiencing an equilibrium state between themselves, rather I forming the product P. That's why it is called pre-equilibrium approximation, means before formation of product P, both the reactant and intermediate I are in a state of equilibrium with respect to each other, and the condition, mathematical condition for this is K minus 1, or the reverse rate of formation of reactant is higher than the rate constant for formation of product P. So if they are existing in equilibrium, there should be a equilibrium constant. The equilibrium constant is the ratio of forward rate constant divided by reverse rate constant. So forward rate constant is Ka, reverse rate constant is K minus A, and capital K is the equilibrium constant. In terms of concentration of the species, I can write I, concentration of intermediate I over concentration of reactant A. So if I rearrange, I can get an expression for concentration of intermediate I. So in all the cases, my aim is to find out what is the product concentration. My final aim is to find out how much product is forming at certain time t. So the rate law for product is dP over dt is equal to kBi. The rate law for product formation is what? kBi. Kb into I, concentration of I. So Kb is there and I is there. In place of I, if I replace this expression, in place of intermediate concentration, if I replace this expression Ka over K minus A, then Ka and K minus A is the equilibrium constant. So I will get an expression in terms of Kb equilibrium constant into concentration of A. And again, concentration of A is known. If we further integrate this expression, then I will get an expression for product P at any time t. This is the differential expression for product P. If I integrate this expression, I will get an expression for product P at time t. Again, the product P depends upon Kb and Ka and K minus A. So with this, I will stop here. Next session we will discuss chain reaction.